Good morning, guys. Just going to do a quick little video here just to progress things forward, hopefully in the right direction. Hopefully no one's gotten confused so far, and hopefully we can get everyone on the same path and that there's no issues. Please feel free to email me or in lab class, bring up any questions you may have about the lectures that we are doing. Today I want to start looking a little bit at our inductive loads, not just looking at resistive, so maybe get a little into inductive, a little bit of capacitive, and then also the relationship between our inductive, capacitive, and resistive when it comes to three-phase power supplies. Obviously, when we're looking at an inductive load, this is going to be inductive load in delta. Now we have three inductive loads rather than resistive loads. And when you're looking at just the inductive load by yourself or by itself, none of the calculations really change at all. You're still looking at your voltages. So in delta, if I were to ask you what's the relationship between your phase voltage and line voltage, and hopefully up to this point you can kind of say that they are the same. And when you're looking at power, as we know, is going to be measured in bars, either inductive or capacitive, depending on what we're looking at. Obviously, in this case, we're going to be looking at inductive bars, but the calculation to find those is the same. We also won't be looking at, in this class, millihenries and or henries and farads. Mike Mankulich will be looking into that or going through those things, I believe week 6 or 7, maybe a little later than that. So don't have to worry about that now, and just like we said for resistive loads, that all of our loads are going to be balanced. So all three phases are going to be balanced in the circuits. So we have a delta connected inductive load. So let's just assume a value rather than putting in a circuit yet. Let's look at 600 volts for a line value. And we'll just write down below E phase, E line, E phase, E line, I phase, I line, and our power. So if we were to take a meter and we go to put a meter across these 2 points, obviously if I measure here to here with a voltmeter, line 1 to line 2, line 2 to line 3, or line 3 to line 1, I'm going to read 600 volts, which is our line voltage. When I come down to my inductive load, so I'm going to be looking at just this phase by itself, if I follow with my meter, these points here, right, are the same as that point electrically, so our voltage will still be the same. So I still will see 600 volts, obviously nothing changes there. And let's assume we have 10 ohms per phase. That's 10 ohms there, there, and there. So when we go to look down or break down and look at each phase individually, we can see that, and as we know, volts divided by resistance is equal to current. So 600 volts divided by 10 ohms, and that's going to give us a current of 60 amps. Sorry for making that a little tight, but we're looking at 60 amps per phase. 60 amps, 60 amps, and 60 amps. So we can put these values in underneath. So E phase is 600 volts, E line 600 volts, and our I phase we see is 60 amps. And as we've discussed in past classes, when we go to look at our line values, that's where the difference is going to truly come up. So if we have 60 amps being drawn by that phase, and 60 amps being drawn by that phase, obviously it has to be a larger value that that current is split from. So if we come back to our terminal values, or into the line, we would have some larger current that came over and then split, sending 60 amps this way, 60 amps that way. But as we know, because it's three-phase, that those line values, or phase one and phase number two, are not 180 degrees out of phase with each other, they're 120 degrees out of phase with each other. So it won't be twice as large the value, but as we've discussed in past classes, that value is going to be √3 larger. So if I want to find what my I line is, I'm going to do 60 amps times √3. And we plug that in, we get 60 times √3, or times 1.732. And we get a value of 103.92 amps. And we can plot this down here. 103.92 amps. Each phase obviously would still go with your single phase values that you've calculated up to this point. So those never change. And the rules in a Y configuration doesn't change from inductive to resistive. Where the issue comes and where things get changed up and where issues can happen is when you end up comparing a inductive to a resistive load, or an inductive to a capacitive load, where you're going to have to do some extra calculations, but we will get into that shortly. And then now the formula. So obviously our power, we're going to be calculating a value that's in VARs. And same way as we did before, you can either do E phase times I phase times 3. So you take the power per phase times the voltage of 600 volts times √3. And that will give you the answer. Or you do our line values, you can do E line times I line times √3. Both of those will get you to the same conclusion. So let's just do our phase values for E's. We've got 600 volts times 60 amps times 3. So 600 times 60 times 3. And we get a three-phase power of 108 kilivars. So that equals 108 kVars. And that would be inductive. So that's how you'd figure out your inductive power in the circuit. All right, now let's actually put this in the circuit with some other values, with some resistive values, and see how we end up handling that. I'm going to leave that guy the way it is, because we've already calculated that, just for saving time. So we said that that was 108 kVars, and sorry, I'm getting down near the bottom of the board, but 108 kVars. And let's bring this into a circuit. I'm going to have a resistive inductor. Let's do resistive load number 2. Load 2. Load 1. And our 3-phase power supply. And this 3-phase power supply, as I said, you could assume it's a transformer, or a 3-phase transformer, or an alternator. Let's make a little more sense, possibly. What I will end up doing later, I'm gonna stop, once you guys are a little more familiar with these drawings, I'm not going to draw all the lines in anymore. They aren't required, but for now, I'll just keep those in the circuit. And I do realize I did change the phasing from one side to the other, but maybe this is a lighting load that I wanted to use a different phase. Doesn't really matter. I was gonna say a motor, and the motor is going backwards, but then remembered I had drawn it as a resistor, so that one's on me. So I've got still 600 volts as a line value from here to here. So I can write my E phase, E line, I phase, I line, and my power. And remember, power in this case is measured in watts. And let's assume for this one that we're doing, let's do 10 ohms. No, let's do something different. Let's do 20 ohms. 20 ohms per phase. Our 600 volts, when we get to our Y-connected resistor, we've got 2 loads that are splitting that voltage. However, as I stated before, they're not 120 or 180 degrees apart. They're 120 degrees apart. So we're going to be looking at a value that's √3 smaller. So if we do 600 volts divided by √3, we get a value close to 347. I think it's 346.2, 600. Yeah, 346.4. It's just 346.4. Let's just keep that the way it is for accuracy. So we have a phase value of 346.4 volts. Our line value, as we said, was 600 volts. Now let's look at our phase current. Well, phase current, you need to look at obviously the relationship between the ohms and our voltage. So current is going to be our E phase divided by our resistance. So our I phase is going to be 346.4 volts divided by 20 ohms. And that makes our I phase about 17.3 amps. Okay, so 17.3 amps. So that 17.3 is going to be at phase number 1, 2, and 3. So I'm going to write just 17.3 here and 17.3 amps here. Because I only stuck with 1 decimal, I'm just going to keep 1 decimal when I come to my currents at this point. I'm not overly looking at, and at the end of the day, I'm more concerned that you know how to go through the process of doing the math more than how many decimal places you have. Typically, it is good to keep 2, but I did start with 1, so we'll just keep it at 1 decimal. So we had 17.3 amps. If I were to take an amp clamp, and I took my amp clamp and I put it on that phase, I would read those 17.3 amps. When I come up into my line values, notice that unlike in delta, where I had 2 loads that were splitting that current, that value is the exact same. I haven't added another coil to it. It's the same point electrically at this point as it is up here. So I can assume, and if I were to just carry an amp clamp, there's nothing else being added in. So my phase value and my line value for current are going to be the same, and that holds true and goes along with what we talked about, how that current in a Y configuration is the same in the phase as it is in the line. So we also have 17.3 amps in the line. And then that's where it stops being the same. If these were all resistive loads or all purely inductive loads, I could add all my line currents together and that would be fine. So if this was a resistive load, I could take my 103.92 and I could take my 17.3 and I could add those values together, and then that would be the current that's seen at my power supply or alternator, right? But we can't do that, and as you guys know, going through intermediate and even refreshing on a bunch of the stuff at the start of intermediate, or sorry, start of advanced, that all that, everything that you're going through is, when it comes to a resistive and capacitive load, or a resistive and inductive, or you're doing an RLC circuit, that we have to plot it on a vector. We have to look at the, we have to use Pythagorean theorem and look at our, if there's inductive and capacitive load, look at our net reactance between the two. So that's where we're going to get into now. So I can say that yes, at this terminal, I have 17.3 amps, and that's where that ends. I can say that at that point, I have 103.92 amps, and that ends is when we go to put those two values together. And we are going to plot it over here. Because we are in parallel, not in series, our capacitive values are going to be up here, and our inductive values are going to be down here. So we're going to be doing our current triangle. And remember, in parallel, there's only two triangles you can do. You can do a current triangle, and then you can do a power triangle. So if we look at our chart right now, obviously there's no capacitive portion of it, so we don't have to look at a net value. We're just looking at the inductive. So the inductive value, we're going to be all the way down here, and that is, as we know, is 103.92 amps. And we are looking at a resistive is along the x-axis, and the resistive, if we plot that out, is going to be, we've got a value of 17.3. So I end up having a triangle that sort of looks like that. So this guy here, I'll put over here, and we've got 103.92 amps. So that is the current, our inductive current. that's our inductive current. Our resistive current is 17.3 amps. And now, with this, we can look at the hypotenuse from one side to the other. And if we look at that value is going to be our total current. So our that's going to be our I line at our power supply is going to be the hypotenuse of that triangle. I know that's an ugly looking triangle, but that's what it gives us. So now I want to use Pythagorean theorem. I'm going to erase some of this just to clear up a little bit of room. All right, and I'll just make that node here, and we'll just say that we had 103.92 amps here from our inductive, and we had, coming this way from our resistive, we had 17.3 amps from our resistive load, coming back to this point and back to the power supply. So if we were going to do Pythagorean theorem on here, I'm going to redo this triangle over here, make it a little more legible. I know this isn't to scale, 17.3 amps and 103.92 amps. We want to look at Pythagorean theorem, so we're going to look at a squared plus b squared is equal to c squared. So I'm going to do 17.3 squared plus 103.2 or 92 squared, and that's going to equal our c squared. And I hope that's not too small for that in the video. So we have 17.3 squared plus 103.92 squared. And we get a value, so c squared is equal to 11,098.6564. And just leave that value on your calculator, because what we're going to do is, obviously, to get c by itself, we have to square root both sides. So I'm going to square root this lovely number. So if we go and take if we go to square root, the 11, and I lost on the calculator, 0.6564. Square root of that is 103.35. So that value is 105.35 amps as our hypotenuse. And when you look at this, when you go and calculate everything, if we look at these values, we know before we start that this value here has to be greater than those two, because it's the longest side. And as I said, I believe in the last class, is always make sure before you punch things into your calculator that you have an idea of roughly what that answer should be. Because I could put maybe the wrong value, or I hit the wrong value on my calculator, and it could very much skew those values. So try to get an idea of what it should be, and with it being slightly larger, because this one side isn't very long, that does make sense, of the 103 or 105.35 amps. So that value would be the value that is seen here. If I put an amp clamp here, it would say 105.35 amps. Remember, we used line values, and you can only use line values to calculate this out. So I have a line value here from my resistive load, I have a line value here from my inductive load. So if I'm using a line value and line value, this value here has to be a line value. When you're looking at Y-connected power supplies, if you forgot this point, you still would get the answer right. But if we were looking at a delta load, you would get it wrong, because as a resistive load, if I put an amp clamp here, it's gonna read 105.35, and if I came down to that phase value, because there's not another coil producing it here, my value per phase is also going to read 105.35 amps. So I could get away with assuming that the value is 103.35, but if this was a delta connected alternator or a three-phase transformer, when we got through a load, that would end up being split, right, between a couple loads. So that 103.35 would actually be a smaller number when it came down into load. So always keep that in mind, that it is a line value, and you may have to change it before you go down, into that alternator. So yeah, so that's everything with looking at current. So we can say that it is 105.35, and I can now bring these values over. We will erase these. And we have our E phase, I can write down E line, I phase, I line, and our three-phase power. All right, so our phase voltage. So let's start with line voltage, 600 volts. Remember, because this is in Y, we need to be √3 smaller because of what we talked about over there. So we have 346.4 volts. And we just established that our phase and line values are the same, 105.35 amps. And then is the question about the three-phase power. And when we look at three-phase power, there's a couple different ways we can go about figuring this out. We can take all of our individual powers that we calculated, and remember I said that there's a current triangle and a power triangle. We can plot those, or the other thing that we can do is we can take all these individual values that we have and calculate out what our three-phase power is. And remember, three-phase power, anytime you have an inductor and a capacitor in with a resistor and or, capacitor and or a inductor in with a resistor, we are now going to have a volt amp power. So we've got our true power using resistors in watts. Our inductive is going to be a VARs, power in VARs, and then our total power is going to be a volt amp. So let's just calculate this out using the formula. And remember the formula, well in this case, for three-phase power, so our volt amps is going to be E phase times I phase times 3, and then technically in this case we are also going to look at value times the power factor. Anytime you get involved when you have an inductive portion to it, you also need to look at what your power factor is going to be. Okay, let's simplify some of the things here. So we have an inductive power. Let's just calculate our resistive power first before I get rid of all this. So resistive power, we're going to do our phase voltage of 346.4 times our phase current of 17.3, and we're going to times that by 3. So you should end up getting a three-phase wattage of 17.9 true power. And I'm gonna come over here. So our triangle, obviously the shape of the triangle is gonna look the same. Right, a little skewed. I'll just draw this out again. Draw the line up here higher. So this is a resistive, capacitive, inductive, and so we're gonna come out, we know that we have our true power is 17.98 kilowatts. And we've got our kVARs, our inductive is going to be 108. kVARs, and then we need to look at what our hypotenuse is, and that hypotenuse is going to be our total three-phase power. So let's do, if you want to know what the formula is without manipulating it later, is the square root of a squared plus b squared. Okay, so that'll give you the answer right away if you want to do it. So you could do the square root of a squared. So a squared, we're going to do 17.98. So I'm going to do 17.98 squared plus 108. So that's 17.98 kilowatts squared plus 108 kVARs squared. Make that a little more legible for you. So 17.98 kilowatts squared plus 108 kVARs squared. We get an answer of 109.49 kVA. So that would then be over here. Our hypotenuse would be 109.49 kVA. And the reason why I like doing both is that you can check your answers as you go, so you can do it this way, and then you can come back and then calculate your individual values. And obviously your individual values, if you calculate them out, they should be the exact same as what the it is when you end up plotting them. Okay. So if we look at this, we end up having 105.35. We're going to use phase values times 346.4 times 3, and we get 109.48. So what I did, so these values have already taken into account the power factor. So what I'm going to be pounding out technically right now is that. So what I end up doing is I took 105.35 amps times 346.4 volts, and then I times that by 3, and that gave me a value of, I know this is crowded, 109.48 kVA. which is very close to that. So when you get done everything should look very close to the same. Obviously, with rounding a couple of decimal places, either higher or lower, you end up getting that slight variance that you do there. Okay? So once you get all that done, the only other thing that I'm going to show you, I know it's been a lot, I'm just going to add one more thing at the end, is that I can calculate what my power factor is now. And if you remember, power factor was equal to our true power over our apparent power. Remember, our apparent power is our voltamps, true power is our watts. So we get our true power was 17.98, or is 17.98 kilowatts. Our apparent power is 109 let's use this one, 109.49 kVA. And as I said, next class I'm going to have handouts for you. And we end up getting, and I'll move out of the way shortly, if I end up doing this, we have 17.98 kilowatts divided by 109.49. I get a power factor of 16.42. So 0.164 or 16.4% for our power factor. And that makes sense because the majority of this circuit was inductive and very little resistive. Obviously, if our resistive values were higher, our power factor would be better. And what I'll go into in the next class is adding capacitive load into that, which is going to end up offsetting that net reactance. So our power factor is going to be improved. Okay, that is everything for this video. Hopefully it wasn't too much, and I'll see you in the next one. All right, bye.